Renee. Yes, welcome everyone. Very nice to have you. Welcome to Leiden, also for many of you. So it's a pleasure to have Renee here today speaking in our differential topology and geometry seminar. And she will talk about manifolds with odd Euler characteristics and higher orientability. Was it correct?
Yes, thank you. Perfect, thank you. Thanks so much for letting me speak here. I've really tried to make this first hour very accessible. So I think many people might be more familiar with the objects I talk about from like a sort of differential geometry point of view, but I'm more of a like algebraic topologist, like multiply theory and stuff. So that's sort of my point of view. So I'll start with this is sort of history of algebraic topology in a way. So how do we develop homology? Euler wrote up this formula for polyhedra that they have. If you take a polyhedron, and you take the number of vertices minus the number of edges plus the number of faces, then you always get 2. So this might have already been noticed by the Greeks for Platonic solids. So at least for Platonic solids, it was already written down in 1537. But Euler sort of is quoted for it because he made a thing out of it, but he didn't give like a rigorous proof. So Cauchy worked on gave a proof in 1811. So then Riemann in 1857 invented the concept of genus, and he thought of like to sort of reason why this is Euler characteristic is an invariant. We now know it's because all of these polyhedra are really spheres topologically. But we can also think of genus G surface. So, for example, a donut or a torus or a 2-hole torus. So he invented this concept of thinking about surfaces with higher genus, and he showed that order characteristic. If I take a surface with genus G, like the G. But this is like the first, like the Euler characteristic is the most, the first topological invariant. So it takes a decomposition where I look at each dimension separately, and then it combines them into one number, and then I show that this number is invariant of the space up to deformation. But Betty, in 1871, showed in fact I can find invariance per dimension, and he invented the so-called homology numbers. It's a number of holes in every dimension, and he showed that like he construct something that's show that this is an invariant too. We call these now the Betti numbers. So, for example, if I look at like a sphere, I don't have any sort of one-dimensional holes, but I have a two-dimensional hole inside, and that two-dimensional hole is also an invariant of the deformation. So then, in the late 20s, Noether and separately Meyer and Vietoris, they developed this more sort of elaborate theory of homology. So homology groups are sort of groups that you assign to a space in every dimension. such that like with coefficients in a certain group. And if that group is a field, then actually the dimension corresponds to these Betti numbers, these homology numbers. So this was like sort of one area of development of algebraic invariance, or of topological invariance, and then another sort of different strain was homotopy. So Poincaré in 1895 first defined the fundamental group. Okay, so the fundamental group is a homotopy class of base maps from the circle into this. So it was noted that this was very interesting, that like a non-abelian group, like it's potentially non-abelian. And if I take the abelianization, then I get back the first homology group. So that was sort of seen as a very fundamental part. And then, of course, it's sort of quite easy to generalize this to higher dimension. And then you can take multiple classes and spheres into space. But actually, when Czech first published this, it was recommended to retract this on the advice of Hopf and Alexandrov, because these higher homology groups actually are abelian, and they thought of fundamental group is like the non-abelian version of homology, so that's what homotopy groups are supposed to be like. But it turned out this was the right notion. So when we look at spheres, they were like spheres are sort of seen as like the most basic, easy topological objects, or like manifolds amongst these ones. So if I look at homology of an n sphere, then I get that this is the integers dimension n and 0 otherwise. Okay. If I look at the multiple groups of the sphere, well, I get the integers in dimension n, and I get 0. It's smaller than n, and this is quite easy to see. If I want to map the circle into a sphere, it's easily contractible. So it was believed that the multiple would just be sort of would reflect homology, and that higher dimensional homology groups of spheres 0. Just believe. Okay. So it gives a great shock to the community when in 1931, Hopf found a map from S3 to S2 that was non-trivial. So this was the Hopf version. And it looks like this. It's a fibration with base space S2, fibers S1, and the total split looks like S3. So S3 it can be viewed as like an S2 worth of S1s. So what does this look like? Well, I can think of being an S3 as sort of like inside just a 3-ball, and then I imagine another 3-ball being sort of glued on the outside, right? So in every direction. So I'm at the North Pole, and in every direction I sort of at some point reach the South Pole. What does it look like? Well, imagine that I take one circle that is going from my North Pole to my South Pole. Okay, just pick one, and now imagine these being put together somewhere. And I pick some other S1 that should be transversed to it. So let's say it's like this. Okay. And now what I can do is I can pick a torus around this one. See whether I can draw this in a nice way. That's a torus. And then I sort of fill out this torus with circles. And I use circles that go once around every meridian. So for example, it goes like that. And go all the way around. So that. Okay. And now I can fill up all of the space in between by taking torus and toya different. So that's right again. And that's how I fill up the whole space. So now I've seen that I've like filled the whole of S3 with circles, and none of them are intersecting. So why is this an S2 work? Well, if I pick sort of a half cap here, so it lands in the middle circle that I selected, then every S1 is hitting this surface once, except for this one on the boundary. So I collapse this boundary to one point, and then I have one S1 for every point. Right. So
can I ask a question?
Yes.
So when was check? When did he define this?
Yeah, so I think he defined this like the paper was I think in 1932, but I think that was the one that actually he did publish. But I haven't like written like I've just read Wikipedia. You have this history like
Okay.
history books if you know better than
No. It was, I was just wondering what he does with this paper, like because does he compute anything because that's super hard, right? So or does he just say, well, it's a group and
well,
one plus some.
I think maybe he just said it was a group and it's noted that it was a Abelian.
Okay.
But I really don't know. I don't. I don't need to base it on. I just know that like, well, at least it's cited everywhere that it was a big shock that there was a non-trivial map from S3 to S3, which it is really, right? Like, I mean, the first time I heard about this, I was in shock. So we see that any two S1s in this are linked. I mean, they're linked exactly once. The form would assign a half link. And we can generalize this as to the Hopf invariant. So the Hopf invariant H of a map M1 to Sn is the linking number of sort of I pick two generic free images. So it's not too difficult to show that this is an invariant of homotopy of the map, of this map. So that shows that this map is really non-trivial. So we can't. Also, I mean, we sort of know that F3 is not a product of this one. Right. So go here. So Adams in 61 shows that exactly 4 that Hopf invariant. As the Hopf invariant 1 problem that's readable.
Yeah, I think it's good.
Okay. So S0 goes S1 to S1. This is just a double coupled circle.
Actually, Renee, can you do it slightly bigger? Because indeed, this one is a bit small.
So my hand directly is not.
Nothing.
Now we have the one at Hopf found. we have S3 goes to 7, so that's 4, and S7 goes to S15, so S8. And these exactly correspond to the existence of the reals, the complex numbers, the infinities, and the optimals. So it's quite easy to see why. So these are what's called norm division algebras. Algebra over the reals. So let me tell you at least why a norm division algebra over reals gives rise to such variation of spheres. I think that the last one's probably too far, right? Or
Maybe, yeah.
They already is.
Yeah, I think that one is good.
Okay, so a norm division algebra is something that has two properties, namely, first we can divide. Can you see that?
Mm-hmm.
So if we have A times B is 0, then A is 0 or B is 0. And secondly, well, if we want, and the norm meets with the product. So it was known already, Hurwitz proved, I don't know when exactly, that they're exactly 40. So suppose that I have K, which is one of these division algebras, so like just think of the complex numbers in your head. Then what I can do is
Okay, Renee, now they're complaining that this board is hard to read. Maybe let's abort this board and let's just use like the green metal ones or stuff. Sorry.
Can I add something quickly?
Yeah.
Why is it is it easy to see that the Hopf invariant is well defined? In the sense that if I pick any two high beds, the linking number is the same.
I don't know. I mean, here I really have like a fiber bundle, so hypersymmetric. I don't know.
If you choose different of these things, then you get an embedded cobordism. And sort of like these numbers in the end come from, okay, I'm filling up my circles by disks, and then I would have a cobordism of those things. And then you have to sort of see that you, like the intersections that you get, they're like one-dimensional things. And then you must do the same. But I can sketch it out.
Well, it was like, I mean, I haven't thought of doing it, but like that like higher, it's like exactly where it's in 2n minus 1 to Sn. Yeah. Or
That's
like,
a dimension count.
yeah. Linking actually happens.
Okay.
It's the standard differential. Yeah, the thing that you do in different topology.
What exactly is that of a Hopf vibration? Do you mean everything?
Oh no, I just mean like so okay. For Hopf vibration, I mean like maths like this with the variant one.
Right.
Okay, so if I have this a norm division algebra, then what I can do is I can form the projected lines. So I take x and y in place first, and I divide by relation that xy is related to sort of a multiple prime elements in this example. Note that this is a line for Unitarians because they're non-associative, and actually what I'm doing here doesn't work, but there's a different construction. So that allows me to construct just only one and OP2, but not higher. Okay, so
Sorry.
This is really sort of a space of lines. What I can do is I can take a canonical line bundle. So this is just canonical in the sense that every point was defined as a line. So I can take that line over that point. Okay. Well, what are fibers of such a bundle? Well, every line was a copy of K. Okay, so that's. And then in this canonical line bundle, I can now take the unit sphere bundle. Okay, so I have the same base. And now I have a sphere bundle of this line bundle. Every fiber is what the unit circle, which is S K minus 1, if the dimension of K was K. But if I think about it, this is, so I've taken all the lines in K squared, and now I've taken the units in every line. In other words, I've taken all of the vectors of unit norm in K squares. So unit sphere in K squared. So this is S2K minus 1. And I can also show that K pi 1 is always diffeomorphic with a 1 point compact K to the SK. So what I've constructed here is exactly a map of fibration for fiber bundle SK minus 1 to S2K minus 1 to SK. And those correspond exactly to these formulas. Okay, so Adam showed that these are the only maps of Pokemon 1. And they did that using topology, which I want to comment on in the end of this hour. However, these are not the only non-trivial homotopy groups of spheres, higher homotopy groups of spheres. In fact, there are many non-trivial ones. So, for example, if I write down all of the multigroups or a bunch of multigroups of S2, then what pi 1 is 0, pi 2 is given by sort of winding the S2 around itself. So those are predictable. Then pi 3 is the integers generated by this Hopf. And then afterwards, they're all torsion. Pi 4 is Z mod 2. And let me just write down some torsion. Then I get Z mod 2, Z mod 12, Z mod 2, Z mod 2, Z mod 3, Z mod 15, Z mod 2, Z mod 2 squared. I can just name them. Z mod 12 times Z mod 2, Z mod 84 times Z mod 2 squared, Z mod 2 squared, well, etc. So these are really spooky. And higher homotopy spheres are sort of a big research area now. It's like all of homotopy theory around these homotopy groups. So the homotopy groups are also an almost complete invariant of topological spaces. So I call two spaces weakly homotopy equivalents. If there's a map that induces homotopy equivalent or induces isomorphism all homotopy groups, and if I'm in CW complexes, then this is the same as being homotopy equivalents. Okay, so spheres are clearly not the elementary building blocks of bases that people thought they would be. So what are elementary building blocks? Well, here it is. So from the point of view of multi theory, elementary building blocks are elementary plane space. So if I take a group G, I can form space KGM. And this is a space with the property that if I take multiple groups, then these are G elements in N and 0 otherwise. Okay, so note that of course, like in order to form this, if N is bigger than 1, then G needs to be in, otherwise I don't have this. But I can show that these are these exist, and they're unique of the weight equivalence. So just some examples. KZ1 is S1. So the one sphere is the only one that is like nice and higher multiple, zero vanish. If I take a free group, then this is a wedge of S1s. I want to make Z to the N, then I have to add in sort of the torus. So this is the product of the N, which is the N torus. KZ2 is a space called RP infinity. So that when I make sort of these projective planes over the reals, or projective spaces, but then I sort of take a whole limit for and go into infinity. KZ2 is the same thing, but now with the complex numbers, CP infinity. KZ4 is HP infinity. And but note down a lot of like K something 1. So that's also known by a different name, namely classifying space. Oh wait, I wanted to note that like so there's actually quite a nice way of constructing these, namely
Yeah, go on. Sorry, Renee.
Look at the camera.
Yeah.
this thing. So if I have a group G and I'm given a presentation of this group, then I can just take and I want to construct like KGN, and I take a wedge of n-dimensional spheres for every generator, and I attach cells for every relator. And then I have a Moore space, it's called, but then it might have all kinds of higher multiple groups, and then I'll have to like iteratively kill all those multiple groups by like gluing disks to them. Okay, and in general, this will be like infinite dimension. So it is that KG1 is also known as classifying space BG, and there's a different way of constructing this. Maybe it's BG over G, where EG is a constructible space with a 3G action. So for example, this RP infinity, I can construct as S infinity over some production. So S infinity is a limit of sort of the inclusion of the spheres into each other. And these are very nice, so I can give spheres a very nice cell decomposition with 2 cells in every dimension. Namely, I start like that, and I add 2 1 cells, now like an upper disk and a lower disk, and I have the 3 ball inside and outside. Okay. These have a nice F2 action, namely by swapping these two cells in every dimension. And if I quotient this, I get RPN for the n sphere and RP infinity for the infinite sphere. Also, the infinite sphere is contractible. So nice to know maybe that Z2 is also O1 or total transformation in 1 dimension. And right, so the nice thing is that like this construction of a classifying space, that also like what we're doing here is for discrete groups, because we can't add any like topology to the groups because there are multiple groups of some space. So if we want to do something for topological groups, then we can do a similar construction, but we don't get something that has vanishing higher multiple groups, but we still get a similar thing. So for example, I can construct the classified space with the orthogonal group in n dimensions by taking n-dimensional frames in R infinity. This happens to be a graphical manifold with O(n) actin. And then I'll open up O(n) actin. And what I get is the Riemannian of n planes in R infinity. So I'm in R infinity and I take like n-dimensional planes. So this is a sort of generalization of what I was doing before. And now note that what a RP infinity, right, was also linear of 1 plane in R infinity. I'm going a bit slow, so I'm checking whether I should skip some. Okay, so a nice thing about these ideal plane spaces is that I can also use them to represent cohomology. Okay, so if I take cohomology of an plane space with coefficients in the cohomology square and the dimension that before, then if I look at the universal coefficient theorem, so because my space is n-connected, there's something called a Hurewicz map, which links homology and homotopy. And if my space is n-connected, then also my homology groups and cohomology groups will vanish up to n. So this shows that my n-dimensional cohomology group is actually the same as maps from n-dimensional homology. With G coefficients. Into G with G coefficients, I think with integral coefficients. Right. Yes. So, well, also by this Hurewicz isomorphism, the first homotopy group and the first homology group are always the same. So here I just have my n homotopy group, but that was just G itself. So we get that the nth homology group of an invariant plane space is just homomorphisms from the group to itself. So in particular, I have an interesting object here with this identity map. So now if I have a map from a space X into an identified main space, then I get a map in cohomology the other way around. And here I had like a special, I had a special element. So I can take, I can sort of, take F star of the special element in the cohomology, and this gives me a cohomology class for X. And turns out it gives me an isomorphism from between maps from G into its identified game space up to homotopy and dimensional cohomology of X. So, apart from representing cohomology, they also tell me about the structure of cohomology. So if I have cohomology groups, I might have cohomology operations. So for example, taking the cup products of cohomology classes is an operation on cohomology. And I have a more general set of operations on cohomology. So theta is, I call theta in between from M to M prime. The cohomology operation is just a family of functions theta x from elemental cohomology of space X with G differences to prime dimensional cohomology of space with G difference for all space X that is natural with respect to spaces. So that means if I have a map between spaces, then this commutes.
Okay, break the chalk.
But the induced map of cohomology commutes with my cohomology operation. And now, so I have a nice theorem now. My cohomology operations actually correspond to maps between and of instances. So remember, this is the same as M prime dimensional cohomology of the first space, right? So I can take a cohomology operation here and map it to, well, I perform cohomology operation on a map identity of G, because identity of G was an element homology path of the unbroken space. And my homology operation goes from n dimensional to n prime dimensional homology, so exactly I land in this image here. And the other way around, I can construct a map. Well, if I have a map of unbroken plane spaces, then viewing some homology class as a map into an unbroken plane space, I can post-compose with the map of unbroken plane spaces. So this tells me that homology operations correspond precisely to maps of unbroken plane spaces. But I see that, like, in a sense, maybe spheres are not the basic objects or multi theory, but unbroken plane spaces are. In particular, I want to talk about homology operations for Z2 homology, which are schema for it. So I want to write that, like, so these are somehow maps from unbroken places for Z2. So for example, RP infinity, but also like the higher ones, etc. I want to write that because that's quite involved, but I'll just define what they are. So square I takes a k-dimensional Z2 homology class. Take the sine dimensional homology class. And they obey the following. They have the following properties. If I take square of the degree of the class that I'm working on, then this is just taking God squared, which is where the name comes from. Square 0 is just the identity. And if I operate with square I of degree larger than the class I'm operating on, and then I get 0. So if I visually like draw my homology classes, so this would be H0, H1, H2, but I can't have any squares that sort of go from H0, but I could have a square 1 that goes from H1, and have a square 2 that sort of starts from H2, goes like square 2 here. So abstractly, the schema squares form what's known as a CMOD algebra, and they obey the exact relations, which, you know what, I'm going to write in the next one. But they're like a product formula. So another thing that shows that unbroken plane spaces are really the elementary building blocks of spaces is that we can use unbroken plane spaces to build up spaces piece by piece. We can do that in two ways, maybe from the ground up or from the top up, from the top down. Yeah. So I'll introduce the white left hour today and if you can install the pop and pop. Okay, so if X is going to be doubly complex, so we have a tower of doubly complexes that look like this color. So this is a tower of spaces with the following properties. If I take the have multiple groups lower than n, then I get 0. And if I take a multiple groups bigger than n, then they're the same as my original space. And notice the same, but they're the same induced by this map that I have here. And moreover, like every one of these maps is this vibration. And it has fiber given by I multiplication space of exactly the parts a multiple group. So just an example. So first, the first one we all know, because this is just the universal cover. And for example, if I take this space BON, which I told you was Grassmannian of n planes in R infinity, then the universal cover of this, for x1, turns out to be exactly the classifying space for the special orthogonal group, which is also the Grassmannian of oriented n planes in R infinity. So I have a double cover here because I have two orientations for every plane. Okay, so that leads me on to introduce vector bundles.
Sorry. What's the daily example for the two connected cover?
The classifying space of the spin group.
Okay.
So I'll really only be talking about the white tower of BON, and I'll talk about it next year as well. So I think everyone has probably seen vector bundles a lot, but we all think about it in, or maybe a little, but we think about it maybe in a different way. So a vector bundle is something that has to my base space X, and that was a vector space at every point. Okay. But the way I like to think about vector bundles is I think of my space, and sort of most spaces, especially if I have a manifold, but also a nice CW complex, I can embed it in a large enough Euclidean space. So I think about my space, and I think about it as like actually sitting in some Euclidean space. And then I think about a vector bundle as like an actual plane at every point. Yeah. So now what I can do is I can forget sort of the position, and I can only remember what the orientation of that plane was at every point. And that gives me a map from the base space to this Grassmannians of n planes in R infinity. Right, so I specify a plane at every point. So another way that I can think about this is I can take this canonical bundle. So this is a vector bundle over the Grassmannian of n planes in R infinity. That's the same as I talked about before. It's canonically that same vector space at every point. That's specified by space. And then if I have a map here, I can pull back my vector bundle, my canonical vector bundle under this map, which I call the classifying map. And that gives me a bundle over the space. And now I will show that, like, so if in other ways, like any other way of defining a vector bundle, like vector bundles up to some vector bundle isomorphism, is the same as classifying maps up to homotopy. Okay, so This map in cohomology gives me a map the other way. So to every vector bundle, I have a map homology, homology of BGN of BON to homology of my base. And the image of this is called characteristic classes for the vector bundle. And those characteristic classes, they measure how trivial or non-trivial my bundle is. Because imagine if I would have like a trivial bundle, for example, I would pick exactly the same plane over every point. Then this map just maps to a point. So in particular, my image is contractible. So my map in cohomology would better be trivial. So what can these characteristic classes be? Well, for example, if I look at mod 2 cohomology, so the sort of it can only be as big as the domain of my map. So here I have what's called universal winning patterns. Okay, so I have classes WI, where WI has degree I. And these are called the Stiefel-Whitting classes. And then I talk about the Stiefel-Whitting class of a bundle. As I say, well, WI of some bundle psi is by definition the image under psi of this universal Stiefel-Whitting class. Oh, but I had that one, right?
Yeah.
Okay. So for example, if one connected cover of BL, which is just a universal cover, that can correspond to BSLN. So if I have some map into BON that classifies some vector bundle, then I can ask whether this map lifts BSLN. So I can find a map here that commutes. If this is true, well, so BSON has phi1 is 0. And therefore, again, by this array, the first cohomology is 0. So here, W1 vanishes. So if I want to lift here, then W1 of this matrix psi had better be 0 as well. And it turns out that this is no if and only if. So psi lifts, which it means that so lifts to BSON, which means that it can be given an orientation if and only if W1 psi is 0. And in particular, if my psi actually came from the tangent bundle of the manifolds, so X is the manifolds, this is the vector bundle that's the tangent bundle of this manifold, then this manifold is orientable if and only if this tangent bundle, this classifying map lifts, so if and only if W1 is 0, which is a one-dimensional homology class in my manifold. Right. But I want to note that for an n-dimensional manifold, Wn, so the top is the winning class. So we can see that with like these winning classes for manifolds, they give us sort of the geometric properties of those manifolds. For example, orientability, and the top dimensional winning class corresponds to not to the reduction of what's called an Euler class, an integral characteristic class. So this also picks up geometric information and says that Wn is 0 if and only if Euler characteristics even. Something that I want to definitely want to time for is that so there's a connection between Steve classes and Steve squares, which I talked about before. And I'll just say this in words for people that are interested. So Steve classes measure the extent to which the Tom isomorphism for vector bundle is a module map for the Steve algebra. So I can talk about that later if you're interested. So I just wanted to briefly.
We started a few minutes late, so don't have to immediately spell that through.
Do people want me to talk about the Tom isomorphism more?
Sure.
I'm used to being typed quite rigidly. Right, so if I if my so if I have a classifying map or a vector bundle, okay, then I can form something called the Tom space. The Tom space is called x to the power xi, which is actually this bundle of xi, which is just I take like a disk in every fiber, and I force it out by the square bundle of xi.
Your notation now really the vector bundle is the map. It's the set, like on the right.
Yeah. Okay.
But that's fine.
Yeah.
But,
Yeah.
but just to be clear, yeah.
Yes. Yeah. But okay. But I haven't actually like used xi here other than as a subscript.
Yeah. Oh yeah, sure. Well, okay. This is subscript. Okay, I thought you take this bundle in xi. That's okay. That's fine. It's good. I understand for you.
Being xi means that this bundle of xi of the of the vector bundle corresponding to xi.
Mm-hmm.
Okay, so I can think of my Tom space as being a twisted version of suspension. So if my xi is a trivial bundle, then x to the xi is just n-dimensional reduced suspension. Okay. So yeah, I can think of I just sort of have a sphere here, and then I collect the whole sphere bundle. So this is like smashing with the sphere. But suspension. So for suspension, I have the suspension isomorphism in homology. This takes me up and steps in the dimension. So if I have a Tom space, I similarly again have an isomorphism, but it's an isomorphism, but it's not quite as good. So So I can write 5 from my homology of X to homology of this. Something plus n-dimensional homology of top space. So this is called the Tom isomorphism. So I can sort of picture this as well. I started out with a view of my space. It went from a zero cell to or the zero dimensional homology to n-dimensional homology. And then here I go up n dimensions. So this was X. Next to the prime. And here I have an isomorphism. So here, like my zero class goes to an n-dimensional class here that I call the Tom class view. And so remember that's like my zero class couldn't support squares because the dimension is too long. But my Tom class could support any square, could go all the way up, exactly all the way up. And Steve Whitney classes measure exactly what squares are here. So Wi of xi is by inverse of square I plus phi times 0. And so I go to the Tom space, I measure when there's a steel square, and then I go back. So again, this is a different way of seeing that. My Steve-Whitney classes are measuring like how non-trivial my bundle is. Because if it's trivial, then it's just a suspension. And if the bundle is very weird, then I have like a very twisted suspension. And I can measure this by like looking at the action of the Steno autogram.
Minor nitpick, if you write like this, the G should be Z2, or you should shoot something of your bundle. Maybe.
Yeah, sorry, here I take phi of C2.
Yeah, but the Tom's one is only holds like if the bundle is orientable or you're like in Z2 coefficient.
Okay, so just to close off this hour, let me go back to the Hoffman variant. So what Adams actually showed in 61 is that there's no projective plane. Other than for K, this reveals complex number derivatives of your terms. And the way he did was work as follows. So how do I construct this projective plane? So I already told you about like how we built RPN or RP infinity. We take like one cell in every dimension. So now, for example, for complex numbers, I take one cell in every second dimension, and that's how we get this KZ2 for CP infinity. So the way I would have to, the way I build the KP2 is now the dots that I draw are not the homology classes, but they're actually like cells, like CW cells. So a KP2 would look like this. So I have a 0 cell, a k cell for some k, and a k squared cell. And now, if I attach this 0 cell to a k cell, then this is just an sk. And now, in order to attach a k squared dimensional cell to this sphere, I need to provide a map for the boundary of this 2k dimensional disk to sk. In other words, this is a map from sk to -1 to sk. And you can show that this map that I used to attach this cell, it has a Hopf invariant 1, precisely. So let me call it not that. So Hopf invariant f is 1. Precisely if I have homology the homology ring of this cell complex is given by I have a map some class A here and class B there. So I can so in dimension k, I have a class A, and then in dimension k squared, I have some class B. And the only question that I can ask is, what's the relation between the two? So we can show that this map as Hopf invariant 1 is equivalent to the statement that B is A cap A. And this is exactly what we want in order to produce a k pipe. So this is also square k of A. Okay, so what we're really measuring is whether there is a steamroll square there. And now what Adam showed in his big paper 61 was that if k is bigger than 8, then square k factors over so-called secondary operations. So there's sort of even more cohomology operations that are not completely defined. They're defined up to something, but they have to be there. And if I know that this square is a factor over something, then there has to be something there. So he showed that such a cell complex can't exist, and that's how he showed that there's no one of the one. Okay, but this is the first one.
First part. Maybe talk.
Maybe I haven't. Okay, so I think I'm being dumb, but I don't even understand the statement of the theorem. So there is no KP2 unless K is the okay, but I mean, what else could K be? So you have like the
Right. So what I mean is that there's no cell complex that looks like this. So there's no CW complex X or like Poincare complex. Cohomology of X, let's say integrally, is Z and over A.
no thanks.
So it's something that would play the role of being a